differentiability is our next lesson. Okay, a derivative of a function cannot be taken everywhere. To be differentiable, a function must be continuous and smooth, either the whole way or through a given interval. Okay, so derivatives fail to exist at corners. Here's an example above, which, if you can tell, that looks like the absolute value of x. Okay, that makes a corner at 0 there. A cusp. Okay. Then we have vertical tangents. And discontinuity, which in this case, this is a jump discontinuity, but really all of those discontinuities stand. Which, let's write those out. So we have jump, removable, and infinite. Okay. All right. So, determining differentiability. That means you can differentiate the function. So one way to tell if you're given a piecewise function, if it's differentiable, is to look at the left and the right hand derivative. If they are not equal, then the function is not differentiable. Okay, otherwise, in our other examples, we'll look for a cusp, vertical tangent, or some kind of discontinuity, which we've already learned how to do. Okay, so let's look at example 1, and that is a piecewise function. So we're going to take the left hand and the right hand derivative, which means, well, the left side derivative would be the less than 0, and the right side would be greater than or equal to 0. Okay, and let's see what they end up being at 0. Okay, so for the left side, let's find that f prime. Okay, so that's the limit as h approaches 0 of, well, our f of x on the left side is 2x. So we'll do f of x plus h, which is 2 times x plus h, minus f of x, 2x, all over h. Okay? And now this is a much easier derivative than you've probably seen, but that becomes limit as h approaches 0 of 2x plus 2h minus 2x all over h. Okay? And so your x's cancel. And we get 2h over h, and the h will cancel. So this limit is just 2. Okay, so this f prime at 0 for the left side is 2. And if we take the derivative of the right side and get 2, then it exists. However, if we get a different value, then it's not. Okay, so let's take the right f prime of x, okay, when f of x equals x squared. So this is our right side of the function, and we'll find that derivative, okay? So that's the limit as h approaches 0 of f of x plus h, which is x plus h squared minus x squared all over h. Alright, so that equals the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. Those will cancel. And let's factor out an h. So it'll be h times 2x plus h all over h, and those cancel. Okay? Alright, so now we can take the limit. So these are gone. And since we're not dividing by 0, I'm going to take the limit in one step also. So cancel the h's and plug in 0 for the limit. So that would be 2x. Okay? And so if we're actually taking f prime at 0, that would be 2 times 0, which is 0. Okay, and that's your right side of this piecewise function. So the right side is 0, the left side is 2. So no, right hand derivative does not equal left hand derivative. Okay. Alright, so that's an example where you're just testing to see if the derivative exists. Okay. Let's look at example 2. So it says find all the points in the domain where the function is not differentiable. So it's telling you it's not differentiable, okay? And this would be the absolute value of x minus 2 plus 3. If you want to graph that on your calculator, you can. But basically, this is a regular absolute value graph, like if you think of the parent function. Moved up 3 and right 2. Okay, so it's moved up 3 and right 2. And so this is the graph of f of x. Okay, and so you can see that there's a cusp, or a corner, excuse me, somewhere along there, okay? And it's actually at 2. So that's where it's not going to be differentiable, okay? Basically, what you have to do for absolute value functions is you set the inside of the absolute value equal to 0, and that's where your corner is going to be. Alright, so that's the only point in the domain where the function is not differentiable. X equals 2. Okay. Alright, so next one, find all points in the domain for which the function is not differentiable. Okay. And this goes back to our discontinuity, which we've talked about. So basically where a vertical asymptote or a removable would be. So if we look at factoring the numerator and the denominator, let's see what happens. So this f of x is x plus 4 times x minus 4 if I factor the numerator. And the denominator, so that would be x minus 5 and x plus 1. Okay? So nothing cancels from our factors, so we're not going to have a removable discontinuity. Therefore, we're just going to set the denominators factors equal to 0. And that will tell us where we have infinite discontinuity, or we have a vertical asymptote, okay, which would be an infinite discontinuity. So x equals 5, and then x equals -1, okay? Those are your values where the function is not differentiable. And why is that? Because they're discontinuous there. They have an infinite discontinuity, okay? And that was part of, if you go to the top, whoops, that's one of the places where it's not differentiable. Okay, let's go to the back. So types of failures of the derivative, meaning you can't take the derivative at these points. Okay, the first one says if the limit as h approaches 0 does not equal f of x, then f of x is discontinuous at x, and therefore you won't be able to take the derivative. Okay, and that's a removable discontinuity. The limit doesn't equal the f of the x you're given. Okay, that would be a hole in the graph. All right, so your next type, if the limit as h approaches 0 positive, so from the right side, this is just the derivative. So if the derivative of the right side is not the same as the left side, equals plus or minus infinity, that's where you have a cusp at that point. So if you're getting infinity, that would be a cusp at that point. Okay. And don't forget, infinity is often 1 over 0. That would go to infinity, plus or minus also. So the next one is a corner at that point. And this is what I was confusing. Where the left side does not equal the right side, that will be a corner. Okay. All right, and then if you're just taking the limit and you're getting positive or negative infinity, then vertical tangent. Okay, those are your type of discontinuities. Well, not necessarily discontinuities, but where your derivative will not, it will not give you a value, okay? So, last example on these notes, and we'll work more with these before we move on. Let f be the function below. Which of the following statements are true about f? Okay, so we have piecewise function here. Less than or equal to 3 is the left side, and greater than 3 is the right side. So we want to see if the limit as x approaches 3 exists. Okay, we've really got to test all these 3, see what's true and what's false to be able to answer at the bottom. Excuse me. So let's try this one. That means the left side is x plus 2, so that limit as x approaches 3 negative of x plus 2 would just be plugging in 3 for x, which is 5. Okay, so our left side limit is 5. Then our right side limit, the function is 4x minus 7. So if you take that limit as x approaches 3 positive, we're still plugging in 3 for x. So that's 4 times 3 minus 7, and that equals 5. Okay? So our left and our right hand limit exist, or they're the same. They're 5, and they exist. So check there, that's true. Okay, and in the same way, we've actually kind of answered the next one. F is continuous at x equals 3. Well, if we're getting 5 on both sides of your function, then also you have to think about the fact that this has an equals to. So it wouldn't be an open circle. That's a check. We're continuous, okay? So is f differentiable at x equals 3? Okay, so to find that, we want to look at the left and the right side limit. Okay, not just, oh, sorry, we looked at the limit. We need to look at their derivative. Okay, so the left side derivative, when f of x is x plus 2, we're going to do f of x plus h minus f of x all over h, and take that limit as h approaches 0. Okay, so that would be x plus h plus 2 minus x plus 2 all over h, okay, which that would be the limit as h approaches 0 of x plus h plus 2 minus 8x minus 2 all over h, okay, and those cancel, That's h over h, which is just going to be 1. So the left side derivative is 1. And now I want to try the right side derivative. And that part of the function here is 4x minus 7. All right, so let's take that derivative. The limit as h approaches 0 of 4 times x plus h minus 7 minus 4x minus 7 all over h. Okay, so this is going to be the limit as h approaches 0 of 4x plus 4h minus 7 minus 4x plus 7 all over h. All right, x's cancel, 7's cancel. 4h over h reduces to 4. Okay. So since, let me zoom out. So since the left side derivative is 1 and the right side derivative is 4, f is not differentiable at x equals 3. They're two different values, okay? So the only things that are true are 1 and 2 only, C. That's it for this lesson.